De Broglie waves. What are a particle and a wave? Light, traditionally thought of a wave, can also behave as a particle. Here we have some properties of light: reflection, refraction, interference, diffraction, polarization, and photoelectric effect. Let us consider the light as a wave. Then, this wave phenomena can explain reflection, refraction, interference, diffraction, polarization, but it cannot explain photoelectric effect. Let us consider the light as a particle. Then, this particle phenomena of light can explain reflection, refraction, photoelectric effect, but cannot explain interference, diffraction, polarization, and all. The analogy of a river. The flowing of water represents the wave. The leaves carried by the river are the particles riding on the wave. Everyday object. The de Broglie wavelength of a baseball is incredibly small, emphasizing that wave-like properties are more significant for microscopic particles. Electron diffraction. Davison-Germer experiment demonstrate the wave-like nature of the electron by showing electron diffraction pattern. According to de Broglie hypothesis, all material particles like electron, proton, neutron in motion are associated with waves. These waves are called de Broglie waves or matter waves. De Broglie wavelength. The momentum of a photon of frequency nu is given by P equals h nu upon c. C can be replaced by nu lambda. Then on numerator and denominator, the frequency is getting cancelled and we get the momentum P equals h upon lambda. The wavelength of a photon in terms of its momentum is lambda equals h upon p. According to de Broglie, the above equation is completely a general one, and this is applicable to a material particle as well. Therefore, for a particle of mass m traveling with the speed v, the wavelength is given by lambda equals h upon mv equals h upon p. This wavelength of matter wave known as de Broglie wavelength of matter. Lambda equals h upon mv equals h upon p. This equation relates the wave character, the wavelength lambda, and the particle character, the momentum p, through the Planck's constant h. Observations. The de Broglie wavelength lambda equals h upon mv, so lambda proportional to 1 upon v. More is the velocity, less will be the wavelength. If the particle moves faster, then the wavelength will be smaller and vice versa. If the mass of the particle is more, then also the wavelength will be less. If the momentum of the particle is more, then also the wavelength of the particle is less. 2. If the particle is at rest, then v equals 0, then the de Broglie wavelength is infinite. Such a wave cannot be visualized. Third point, the de Broglie waves cannot be electromagnetic in nature because electromagnetic waves are produced by motion charge particle. Matter waves can travel in vacuum and hence they are not mechanical wave.